Hello, good afternoon, and welcome back. Class is in session. Now, we need to talk about the weather. Gather round, because this is quite a big curriculum. Knowing weather in more detail is essential for your S3 rating in order to be not just an adequate controller, but a great controller. We have 3 topics to cover today. 1 large and 2 smaller, all about environmental factors and how to recognize them. Effects of pressure and wind, freezing condition, and low visibility procedure. So without further ado, let's start with the big one, effects of pressure and wind. This is such an important and effective piece of knowledge because in order to plan and manage your arrivals, which is the most vital skill an S3 has, you need to know what kind of environmental factors affect the aircraft. It's affecting in all 3 vertices of flight: altitude, speed, and path. The key is to understand each of them and knowing how it affects your controlling. It's all a study of pressure. More specifically, the static pressure and dynamic pressure, the most vital principle of flight really. The dynamic pressure is the one you feel when you put your hand out of a car that's moving. The pressure resulting of kinetic energy. Static pressure is different. Static pressure is the force of the atmosphere upon you. A result of that, you are standing under a big fat column of air all the way up to the end of the atmosphere, pushing down on you from all sides. Luckily, you are made to withstand this pressure on the surface of the Earth. And your altimeter works a bit the same way, which takes us to the first part, the altitude. We already learned about this in the transition altitude and level topic, so let's just recap. On a complete standard ESA day, the big column of air pushing down on you will be the pressure of exactly 1 atmosphere, which is equivalent to 1013.25 hectopascal. Your altimeter is calibrated to this pressure, so at 1013.25 at 3000 feet, your altimeter will show 3000. But sometimes the pressure is higher. The column of air gets heavier. This has no effect on your big bulky airplane, but for your tiny fine-tuned altimeter, the weight of the air pushes the reading downwards, leading to the altimeter under-reading. So then it thinks the airplane is actually at 2,700 feet. So the pilot thinks, well, I need to climb to 3,000. And by the time the altimeter shows 3,000 feet, the aircraft is actually at 3,300. This is luckily to the safe side. The bigger problem comes when the pressure on the day is very low. Now there is too little pressure putting down on your altimeter, and suddenly it thinks that the aircraft is at 3,500 feet. In other words, it is overreading. So the pilot once again thinks, well, I need to descend to 3,000, and by the time the altimeter hits 3,000 feet, the aircraft is actually at 2,500, which is much more dangerous. Therefore, as soon as you clear an aircraft for the first time to an altitude below the transition layer, make sure to provide the QNH, so that nice little finely tuned altimeter shows correctly. There are also considerations in regard to temperature, but that's not too relevant for you at the control at this stage, and it is expanded upon in the lessons. Also, the wind has no effect on the altimeter either. The next thing though is really relevant and crucial to understand. That is speed and what pressure and wind does to it. To understand this, we need to go back to our column of air. You see, the pressure decreases as altitude increase. And when you think about it, it makes sense. Imagine this as a big Greek column. If you hold it down here, it's going to be really much heavier than, let's say, if you cut a hole and hold it there. The lower you are, the heavier the column, the more dense the air is, meaning that the molecules are bundled closer together at the bottom of the column. Now, let's leave that for a moment and talk about the speed of an airplane. If you've ever flown an aircraft in a flight sim, you may know that the speed you are flying, the one displayed in your cockpit there, is called IAS, indicated airspeed. But what you need to understand is that this is not a speed we just pretend it to be. In fact, it is a pressure. More precisely, the dynamic pressure we talked about earlier. Because pilots really don't care about how fast they're moving over the ground. They care about how fast the air is moving over the wing. You know, that thing there that keeps the airplane flying. Therefore, you must convert the indicated airspeed, and from there on there are actually an additional 4 types of airspeed this converts to the first two, which are CAS and EAS, calibrated airspeed and equivalent airspeed. It's basically the pressure corrected for errors in readings due to the position of the pitot tube, and further corrected for compressibility of molecule at higher speeds. These are not important. If it is a complex airplane, the instruments are already compensating for this and actually displaying the EAS, calling it the IAS. And if it's a simple aircraft, well, then the difference between these 3 values are so small that it's negligible. But now you've heard about them. The next 2 ones are the ones which are interesting for us. The first one is called TAS, true airspeed. This is where it really becomes a speed. Here we take the density and the pressure of the air into consideration to determine, with a certain indicated airspeed, how fast does the aircraft actually move through the air. It's such an odd thing to understand, so let me try to provide you with a very, very oversimplified explanation of the principle. IAS is a pressure. What is a pressure really? It is in a way the amount of air molecules to travel through to keep the wing up. Let's say that Ryanair here is flying an indicated airspeed of 250 knots, which means 250 nautical miles per hour. Now, let's just pretend for a minute that this also means that he's in fact must fly through 250 air molecules in an hour to have that pressure over the wing. From here to here, he passes through 250 air molecules. The distance from here to here is 250 nautical miles. Therefore, by the time he's passed through all 250 air molecules, he's traveled 250 nautical miles. Therefore, his true airspeed, equivalent to his indicated airspeed, is 250 knots. However, now we go way up to 30,000 feet. Now the air is much thinner here, meaning the molecules are further apart. Now, there's only 125 air molecules from one end of the column to the other one, because they're so much further from each other, because of the thinner air. But our dear Ryanair needs to still pass through 250 of them in order to keep his indicated airspeed of 250 knots, otherwise he's gonna fall out of the sky. Well, no alarm. There is of course another column of air next to it which also has 125 molecules. So now Ryanair just goes through both of them to have 250 molecules traveled, meaning 250 knots indicated airspeed, but you now see that double the distance has actually been covered in this hour. So his true airspeed is really 500 nautical miles per hour, or 500 knots true airspeed. This is just a picture, but it is the illustration of how true airspeed for a given indicated airspeed increase the higher you go up. And it's such an important thing to know when you are planning arrival times and speed restrictions. The higher he is, the faster he's going. Exactly how much? Well, in standard EASA conditions, 2% per 1,000 feet. This means 2% higher at 1,000 feet, 4% at 2,000 and onwards. At 10,000 feet, the airspeed has increased by 20%, meaning our Ryanair flying 250 knots at ground level is flying a true airspeed of 300 knots at 10,000. So be very aware of this when you are planning arrival times, because they are based on a speed which will reduce with altitude. But this is not all. Now we come to the fourth conversion, from true airspeed, which is the distance the airplane is moving through the air, to ground speed, known as GS, the speed of which the aircraft, surprise surprise, moves over the ground. Because this is depending on the wind that is blowing. A tailwind will result in a higher ground speed, and a headwind will result in a lower ground speed. Now let's go up to Ryanair flying at 10,000 feet, which we know means 20% higher TAS than indicated airspeed. Now be careful not to get confused thinking, well, Ryanair will just be blown faster through the air, but he will still cover the same distance, right? So what is the difference? But no. Remember to see it like this. The wind is blowing Ryanair and the air molecules together. So by the time Ryanair passed through all 250 air molecules, the airplane and the molecules has traveled together another 50 miles. Because there was a 50-knot tailwind. This means that the indicated airspeed of 250 knots has become a true airspeed of 300 knots, has become a ground speed of 350 knots. That is how it works. So why is ground speed important? Because that's the speed you see on your scope. All you know is the speed from your radar and how fast he's moving over the ground. So you need to know the effects of wind to have the test, and then pressure and density to determine what indicated airspeed he is flying. Now, for two aircraft flying at the same altitude, the difference from indicated airspeed to test may be different, but given they fly in the same direction, the difference from test to ground speed is not going to be so extreme, because wind generally keeps the same direction over a few thousand feet. Way different though is it when we talk about the path. Last word on this topic. The wind here can make a huge difference. If two airplanes are flying the same direction, they generally have the same wind. However, coming perpendicular or even opposite directions, one will have the gain of a tailwind and the other one will have the resistance of a headwind. And these are important to anticipate, especially as you turn aircraft towards the ILS. Here, you also need to be aware of the wind correction angle. If an airplane is flying on vectors, you are giving headings. If you instruct a pilot to fly a heading, he will fly that exact number of degrees. And if there's a crosswind, well, the wind will actually blow him off course. You need to be aware and be ready to correct this. If an airplane is navigating to a point, he's flying a track. Flying a track, the airplane turns the nose into the wind and flies slightly sideways to keep a constant track over the surface of the Earth towards the point he's navigating to. It's difficult to really calculate precisely, so you need just to do some trial and error and see how much wind correction angle you need. Normally, with a strong crosswind of about 30 knots down the runway, on the base you would need about 5 degrees more towards the wind to keep a clean perpendicular track. The wind correction can also be important with two aircrafts coming from two different directions, because the wind from here example, this guy will fly a lot faster than this guy. So all in all, the conclusion is that pressure decreases with altitude. The higher the aircraft is, the faster he goes for an indicated airspeed. The wind will further increase or decrease the speed of which the aircraft is going. And for crosswind, you need to consider a correction angle to have the aircraft flying the correct track for the heading you have given. Good. I hope you are still on board. Let's move to the next item on our agenda, which is the freezing conditions. This is a weather phenomenon that has an effect on you as a controller that you may need to coordinate de-icing via the various de-icing platforms in Denmark. It starts with a set of conditions which must be fulfilled. There must be visible moisture present. That means rain, snow, or a visibility which is less than 1 statute mile or 1600 meters. That's the contaminant that can get stuck to the airframe. Next, it also needs to be so cold that they actually do stick to the airframe. This is a temperature of 3 degrees Celsius or colder. That's the general temperature limit for having to de-ice or anti-ice. Remember, even if it's higher, or if there's even no contaminant, airplanes still may want to de-ice, so don't just automatically reject requests just because the temperature is 4 degrees. This is because there's two different terms, de-ice and anti-ice. And no, I'm not talking about these fancy switches in a flight deck. I'm talking about these vehicles. There, aircraft are getting a 1-step or a 2-step procedure. First step will always be de-ice, which is removing deposits from the airframe. That can still be present at temperatures well above freezing conditions, as well as, for example, due to overnight parking or very cold fuel still in the tanks. Then, only in freezing conditions, the second step is needed, which is to anti-ice, to allow the aircraft to withstand the freezing conditions for a certain period of time, depending on the severity. Especially in conditions where there's freezing rain, freezing drizzle, fog, or mist, you have to be very well aware of anti-icing requirements. Other phenomena like rain, snow pellets, and snow grains are also possible, but more rarely happens. This is normally something you have to be aware of as a controller, that pilots who are anti-icing only has a limited period of time when their aircraft is clean before they must be airborne. Otherwise, at some point ice will just build up again. Luckily, in Denmark we either have very small airports with short taxi times, or we have airports like Billund and Copenhagen where remote de-icing platforms are minimizing taxi time after de-ice. Then of course there's the second part of the freezing condition. Deposit that may be on the runway, known as runway contamination. These are relatively rare, but may happen in Denmark over the winter. In this case, it's about the braking action, which need to be adjusted to fit with the condition, or alternatively another suitable runway selected. Normally this is displayed in your software through a SNOWTAM, which that can be found in Euroscope for each airport. SNOWTAM gives a long set of numbers which identifies the different information relevant to this SNOWTAM. Here's an example below from Copenhagen, which is produced to give maximum explanation. EKCH 1119080422 right 3/3/5/100/100/750404 with no wet. There's a lot of information here, but only some of it is vital to you. However, what is actually decoded here is the airport, the date and time, the runway in question, the braking action, the coverage, the depth, and the type. And you can see several of them has 3 sections. That's for the different thirds of the runway. So here in Copenhagen, on the 19th of November at 0804 Zulu, on runway 22 right, the braking action is 3, 3, and 5. On the first, second, and last part respectively. The first 2 parts are 100% covered and the last part is only 75% covered. The depth of the first 2 parts are 4 mm and the contaminant on the first 2 parts are wet snow. On the last part of the runway, you can see it's already melted in this situation and hence it just says wet. And that is also why there's no depth reported for this part, because it is just water. Here, of all these things, braking action is the important one, because that one you must know from the SNOWTAM to put into your ATIS, so the pilots are aware that for the first 2 parts of the runway, the braking action is 3. Also, actually, what is even this braking action scale? Well, let's go through it now. It goes from 0 to 6, where the highest is best, and the number 6 will always be dry, as in absolutely bone dry. Braking action 5 is known as braking action good, and more commonly also known as wet. And it can also be used for some types of contaminants such as snow, slush and frost, as long as the depth is less than 3 mm. Once you get above 3 mm, the runway starts getting contaminated and the braking action starts to reduce rapidly. 4 is braking action good to medium, 3 is medium, 2 is medium to poor, and 1 is poor, and 0 is nil, and probably at this point nobody should land at all. These values are normally measured by a car at the airport in real life and communicated to you as a VATSIM controller through the real-world SNOWTAM. This way we can mimic real-world conditions seamlessly. So keep a thought on this and understand how braking action work, and if you are controlling in freezing conditions and precipitation, you may need to check the SNOWTAM for runway condition info. This brings us to the last point of the agenda for today: low visibility operation. Low visibility operations are in effect when visibility and clouds are so low that aircraft can no longer operate on a conventional ILS. With weather like this, we need to activate the low visibility procedures, also known as LVP. Now, what does this mean and what does it depend on? Well, first, some ground rules. Different approaches has different weather requirements and some different minimum altitudes that you can fly to.
Plus 100
is a call out you've heard before, followed by
minimums.
That signifies the lowest altitude a pilot can fly before they must be able to see the runway. There are different requirements for different approaches. There's 2D approaches, such as certain RNAVs, VORs, and NDBs, and localizer approaches that has various minimas starting from 250 feet and upwards. They are, apart from the different visual requirements, they also have a requirement for the base of the clouds to be above their minimum altitude. So, for example, a VOR approach with a minimum of 250 feet is not allowed to be executed if the clouds, for example, are at 200 feet. Then you have a 3D approach, which is an ILS. And yes, a few others as well, but we're not bothered by those here, where you can go as low as 200 feet and is not relying on the base of the clouds to be above or even the visibility. It only relates to the term known as RVR, which is what now? Okay, let's go there. RVR is runway visual range, and it is measured at the airport. Where visibility is defined the distance you can see a black dot on a white background, RVR is the distance where you can see the lights of the runway, which actually does make more sense because that is what a pilot really needs to see. And this can change depending on the intensity of the light and whether it's day or night. A standard ILS without any other considerations can go as low as 550 meters of RVR. Any RVR lower than that, the ILS approach is no longer allowed. And remember, all the other 2D approaches, they will have higher requirements and is hence also out of the question. ILS is the one that can go the lowest in RVR. So what do? There is another feature of the ILS. It has different categories. You probably have heard about them before, but maybe you haven't really truly understood their purpose. ILS Cat 1, which is the standard ILS, is the one pretty much always in use unless the visibility is below 550 meters, so low that it can't be used anymore. Then we move up in category, ILS Cat 2 and later Cat 3, which has two classifications as fail passive and fail operational. Once the RVR drops below 550, you need to activate LVP in order to allow aircraft to do these higher categories of ILS approaches. You do not need to know the specificity of the approach itself, but you do need, however, to think and know which approaches supports this system and which does not. You can find that on the different approach charts. For example, this is an approach chart from Aalborg, where you can see that runway 26 right has both a Cat 2 and Cat 3 approach. So you can run an LVP here, but if you look the other way at runway 08 left, it does not. Meaning that if there's low visibility in Aalborg, you actually must select runway 26 right, even with a tailwind. On the approach chart, you can also see the minima of the approach in radio altitude and the minimum RVR for its use. In all cases, it is a minimum RVR of 300 meters for a Cat 2, 125 meters for a Cat 3 fail passive, and an RVR of 75 meters for a Cat 3 fail operational. With this kind of low visibility, the clouds may be very, very low, or the fog will just make it difficult to identify where the clouds are altogether. Therefore, we have another term called vertical visibility, which is back to that black dot on a white background. However, if you look upwards, that's how far you can see upwards. It is often displayed when fog and clouds blend so much together that you can't really see what is where. And that's it for low visibility. RVR means runway visual range and is the distance the runway lights are visible from. For an RVR of less than 550, a low visibility procedure must be established. Low visibility can only be established where an ILS approach is active and meeting the higher category of more than Cat 1. And vertical visibility is how far up you can see when it's foggy and the clouds are low. That is all from our 3 topics from today. Quite a mouthful, I know, but I hope you learned something. You can now continue with the lesson, which will provide you more specific information and at which airport you will find what. You may now continue. Thank you very much for watching. The class is dismissed.